Hello, good evening. So today we'll learn about prime numbers. Yeah, so before we start with the definition of prime numbers, let's recall the basics of divisibility. So we know in natural numbers, so we'll work mostly in the set of natural numbers. And what are natural numbers? 1, 2, 3, 4, and so on. They are also called as counting numbers. So I denote it by n this way: 1, 2, 3, 4, and so on. And sometimes we work in set of integers where we allow even 0 as well as negative numbers. Fine. Yeah. So we say, let me write with examples. So we say 3 divides 12. Right? 3 divides 12. And how do we denote? So we denote it as denoted by 3 vertical line 12. And what it means is not 3 by 12 or 12 by 3. What it means is this number divides this number. Fine. That's it. So 3 divides 12, or similarly 4 divides 12, denoted by 4 vertical line 12. 5 does not divide 12, right? So 5, I say, does not divide not. So that slash is for negation. So 5 does not divide 12, and so on. Fine. So we say 3 and 4 are divisors of 12. 3 and 4 are divisors of 12. Okay, now 2 sure divisors of 12 are 1 and 12 itself. Fine. Or for every number in general, there are 2 sure divisors, 1 and the number itself. Okay. So for 12, the divisors are 1 and 12. They are in pairs. 1, 12, then 2, 6, and then 3 and 4. Right. So these are all divisors of 12. And those which are other than 1, they are called as proper divisors. So 2, 3, 4, 6, they are called as proper divisors of 12. So neither 1 nor itself, proper divisors.
What means proper divisors?
Proper is neither 1 nor the number itself.
Yes, sir.
So for any number, 1 and the number itself are sure divisors. Okay, so except those two, or other divisors are called as proper divisors. Yeah. And now there are some special numbers where only divisors are 1 and itself, and they are called as prime numbers. Let's define prime numbers. This is essentially all due to Euclid. So Euclid, in his book Elements, which is in 13 parts, there are 13 books, and that was around 200 years before Christ, around 200 BC. So Euclid wrote in his book Elements the basics of geometry, or whatever school geometry we learn, that is essentially due to Euclid. So that's called as Euclidean geometry, and as well as he did basics of number theory, so called as elementary number theory. So all these.
Good morning, sir. Sorry, due to connection issues, I joined late.
Yeah, I have just started with the basics. So today we'll be doing prime numbers, but I have so far not defined prime numbers. I'm just revising, recalling the basics.
So for 1 second, just the previous slide.
Just. Yeah.
Yeah, yeah. Okay, yes. So you can move. Thank you.
Okay, so now towards the definition of prime. Prime or prime number definition. A natural number n greater than 1. You can as well write there in your notebooks, a natural number n greater than 1 is called as a prime number. Is called as a prime number or just a prime if its only divisors by divisors I mean positive divisors. Its only positive divisors are 1 and n itself, number itself. 1 and n itself. Now read carefully. By very definition, we are defining number n greater than 1. We are not taking 1 as a prime. Fine. So another way to look at, so I'll say remarks. By definition, 1 is not a prime. By definition, 1 is not a prime. Okay. Then secondly, another way to look at the definition of prime is, so they have exactly 2 divisors, right? So another way to define prime number is a prime number has exactly 2 divisors. Or prime numbers are those naturals which have exactly 2 divisors. Which have exactly 2 divisors. Fine. And I hope in schools you must have done prime numbers before. So let's start with examples directly. Yeah, shall I go to next page?
Yes, sir.
Sir, 1 minute. Sir, 1 minute.
Okay, yes. Yeah, I'll give one more remark. One which is not prime is called as composite. So I write on next page. Remark number 3. A natural number n greater than 1, again greater than 1, which is not prime, is called as a composite number. So what are composite numbers which have more than 2 divisors? Fine. So again, once again, by definition, 1 is neither prime nor composite. Fine. So 1 is not prime, not composite. By definition. Let's talk about 2. What are the divisors of 2? 1 and 2 itself.
1 and 2.
Right? Yeah, so 2 is prime. Then 3, only divisors are 1 and 3 itself. Fine. So 3 is also prime. 4, What are the divisors?
Sir, it has 1, 2, and 4.
1, 2,
1,
4.
2, and 4. Everyone agrees? 1, 2, and 4. So there is divisor other than 1 and itself. That is 2, or there is proper divisor. So 4 is not prime, but 4 is composite. Fine. Anybody has any doubt with the definition?
No.
No, sir.
Okay. So let's go to first question. Now, what you have to do is in your notebook, write down prime numbers between 1 to 100. Don't disclose any answer. And in chat box, you can write down how many primes are there. Don't write all primes. How many primes are there? That's what you can write in chat box. Okay. So
I joined the class late.
we have just started with primes. Maybe I will show you the earlier slide. Saket, better instead of writing direct answer, you first write down all primes in your notebook because we'll need them later. So if you know the answer, don't write directly answer in chat box that how many primes are there. Better write down all primes between 1 to 100.
Sir, is my answer correct?
Yes, yeah, answer is correct. But it's better you write down all primes in your notebook. Fine, we'll need them.
Sir will check after.
Yeah.
2, 3, 5.
Okay. Yeah. So once again, what you have to do is write down primes between 1 to 100 in your notebook, count them, and in chat box, just write down answer to me or to any co-host, like how many primes are there. Fine. I don't want all the primes, a list of all primes in chat box. Just write down how many primes are there.
Correct.
Yeah. So who wanted this is definition of prime number. In fact, primes, composite, etc. already you must have done in school. So I don't think there is any problem with these definitions.
Can I send my answer in the chat box, sir?
Yeah. Yes.
Sir, if you're checking, then can you check mine also?
Who is that?
Saket.
Yes, Saket, correct.
Sir, is my answer correct?
Yes, I. Dashraj answer is correct, but as I told,
Sir, is my answer is correct?
let me check. Yes, sir. Yeah. So what you have to do is write down primes between 1 to 100.
Sir, is my answer correct? Shrestha.
Yes, madam, sister. Why is no, you have overcounted? Why is overcounted? Sister, it's correct. Ahan, you have missed one prime. And why is has overcounted?
Sir, can you hear me?
Yes, Shivan.
Sir, is my answer correct?
Yes, yes. Someone's audio is on.
Sir, is my answer correct? This is Agni.
Just a minute, huh?
Sir, this my answer is correct. My answer is correct.
Yes, Agnay.
Okay, sir. Thank you.
Okay, so let's write now. And I'll write.
Answer is correct, Arna Shinde.
Just a minute. So now I'm writing the all the primes, and you can check your answer. Fine. Yeah. Okay, so now I'm writing the answer. You can check your answers with that. So between 1 to 10, what are the primes? 2, 3, 5, 7. Is it okay? Between 1 to 10. Just tell me if I have missed something. Between 11 to 20.
Sir, can I see?
Have I missed anything between 1 to 10?
Oh,
11,
sir.
13, 17, and 19.
yes, sir. 11, 13, 17,
1
and
to 20. 11,
11, 13,
13, 17,
17,
17,
19.
19. Then 21 to 30.
23, 29.
29.
29.
23, 29.
29.
29. Now you see the number of primes is reduced. So there are 2 primes in these 10 numbers. Fine. But earlier in first 2 tens, there were 4 primes. Yeah, 31 to 40.
So
31 and
37. 31 and 37.
31, not 33, not 35.
What about 39?
No, 13 into 3.
This is divisible
13
by
is 13 into 3.
Yeah. So 41 to 50.
Sir, 41, 43.
41, 43, and 47.
So now observe that again number of primes is increased here. There are 3 primes.
49 will also come now, sir.
Huh?
Sir, 49.
49 is 7 into 7. So 49 has proper divisor 7. So if you have divisor other than 1 and itself, then that is not a prime. So 49 is not a prime. Okay. Yeah, everyone clear so far? Let's continue.
Yes, sir.
53 and
69. 53 and 57.
53, 57.
53,
No,
57.
53 and 59. 53 and 59.
Not 57.
9, sir.
What about 51?
So it's divisible by 3 and 17.
Yes.
And
3
what
and
about
17.
what about 60?
So it's
This is divisible by 2,
by
3,
10.
6, and 10.
Yeah, that's a good answer. 60 is divisible by 2, right? So see that every number divisible by 2 can't be prime, and therefore you observe that only even prime is 2 itself, but except 2 there is no even prime. Fine. So every prime other than 2 is odd. Every prime except 2
So can I say why?
except 2 is odd.
Sir, can I say why?
Yeah, because
Yeah. So can I? Oh, okay. Yeah, because the definition of even is that it is divisible by 2, and the definition of prime is that it has only divisors 1 and n. So usually in all the cases, all even numbers will have will be divisible by 2, and only 2 will be prime because 2 it is divisible by 2 and 2 is itself. So all the other numbers will be composite, and this is the same for anything, like for 3. So 3 every prime except 3 is every third number, like kind of like that.
Yeah, so you mean to say every multiple of 3 is not a prime, right? Every
Sir,
multiple
that
of
is
because
what even definition is also. So it's
sir, because 2, 3, 5, and 7 are one-digit numbers, and
Right.
there is no other like smaller digit than them. Like this is a one-digit number. There is no such thing like 0-digit and.
So we can use something here. It's called the C-word system.
Yes, we'll see that.
And
Sir,
for-
I have a doubt.
to do that, we need to remove all the multiples of 2, 3.
Yeah, we'll see that. That's our next slide. Okay.
Sir, may I ask a doubt?
Yes.
Sir, can there be negative prime numbers?
No, we don't consider negative numbers because classically this was defined by Euclid, and uh, in those days they were not dealing with negative numbers. So we continued with positive numbers itself. But of course, in higher number theory, higher algebra, one talks of primes, irreducibles, etc., and then you consider positive, negative. Right?
Okay, sir.
Sir,
Yes, Shauna?
sir, what about 0?
No, even 0 is not prime. So at least according to our definition, we are defining only for natural numbers. What are natural numbers? Starting with 1. No, even we won't consider 0 as natural.
So technically 0 is a multiple of every single number because any number into 0 is 0.
Yeah, very good. Yeah. Okay, so how many we have did? 51 to 60. Then, just a minute. I lost my cursor.
Then 61.
61 to 70.
Yeah. So then 61,
61.
not 60, 67.
67.
And not 69 because 69 is 23 into 3.
23. 3. Yes. And 69 anyway is divisible by 3.
Yeah, using the plus thing.
Yeah. So then 71 to 80.
Sir, 71, 73 and
71, 73, 79.
Sir, 71 and 77.
So 71,
71.
73 and 79.
71, 73 and 79.
Somebody said
Even
77.
77.
Should I write 77?
No, 77 is 11 into
Sir,
7.
79.
No, sir.
11.
Okay, 77 is not prime. Okay. 79. Where is my cursor? Just a minute. I lost my cursor. 79. So far good, so far fine. All things are correct.
So yeah.
81 to 90.
80
Sir,
83,
85.
89.
and 80.
83 and
81,
89.
81. What about 81?
So it's
Oh,
divisible.
81 is
It's
9 into
square.
9 or 3 into 3 into 3 into
Okay,
3.
so 81 is 9 9 then. Fine. So there is proper
Sir,
division.
83 and 87.
So 83 and 89. Not 87.
83 and 89. 87 is divisible by
87 is
3.
39 into
Yeah.
29 into 3.
Yeah, it's divisible by 3.
89.
89.
91.
Yeah, and 97 is the only prime to come
97.
from 91 to
91 to 100.
97.
97.
Only one prime 97. Okay, but observe that the pattern of primes is very much irregular.
Irregular.
So in first 10 there are four primes. Yes,
2, 4, 4, 2, 1.
yes, Abhinav? Yeah, so in first 10 there are 4 primes. Again, in next 10 there are 4 primes. The number of primes is reduced here to 2. Again, it's 2. Now it's increased to 3. Again, it's reduced to 2. Here it is 2 again. Here it's increased to 3. Again, it's reduced to 2. Then there is 1. Now, what do you expect? Will the number of primes or will the primes end somewhere? Will the number of
No,
primes
sir.
be finite?
No, sir.
So there's a proof for the number of primes is infinite. Euclid made it.
Okay, so Euclid proved that there are infinitely many primes, and in fact, there are many proofs of this fact. So Euclid was the first one to prove it rigorously, logically.
Sir?
Yes, Aitreya.
Sir, actually, sir, I think that, sir, 100 plus all the numbers from like till 500 or more than 3 digits, they have less primes because the number of digits is like getting larger and larger, so it can be divisible by lot other numbers.
Yeah. So possibly the number of primes gets reduced as the number increases, right? That's what you want to say, right?
So it gets reduced, but it never stops.
Yes, yes. So it's or the rate gets reduced at which it increases, the number of primes increases, but still it will never stop. So Euclid proved how many primes are there? There are infinitely many primes. There are infinitely many primes.
So can I tell the proof for the infinite number of primes?
We won't prove right now, but proof is simple and interesting. Maybe in some other lecture I'll give the proof, but not today.
Sir,
Yes.
yeah, but the more and more you go forward the numbers, then the more and more rare prime numbers become. So if you type a random 7-digit number and check online whether it is prime, it will most probably say no.
Yeah, but I mean that's a different issue. Given and whether it's prime or not, that's a different issue. But right now we are talking of say following. So for example, given n. Okay, so we define that's called as prime number function. So we define pi of n as number of primes up to n. Number of
Oh,
primes.
okay. I thought that symbol was for something else. I thought that symbol was for repeated multiplication.
No. So this is pi. Pi is pi of n. That's how it's pronounced. Pi of n. So it's called as prime number function. And it talks about how many primes are there up to n. In fact, let me
So though it is extremely rare if you go further and further to find prime numbers, somehow there are infinity prime numbers.
yes.
Yeah.
But this function goes slow as n increases, right? So number of primes up to n, that is pi of n. So for example, all of you must have written in chat box the value pi of 100. And what is pi of 100?
25.
Numbers up to 100, and that is 25. Okay, that is 25. Yeah. So tell me, what is pi of 50?
Wait, 4 plus 4 plus 2 plus 2 plus 3, which is
15.
15.
15. Okay, so see that in first 50 numbers there are 15 primes, but in next 50 there are just 10. So the
Yeah.
number gets
And then the next 50 even less.
yeah. So
Because it will be more and more because the easiest way to prove that the prime numbers gaps will decrease in intervals is that you can take a table of numbers. Okay, 2, you scratch it off because it's, you circle it because it's prime, scratch out all the multiples of 2. You take 3, you circulate, scratch out all the multiples of 3. So this proves that prime numbers will come in longer and longer intervals.
right.
So that's called the sieve of Eratosthenes.
Right. We'll go to that. See, okay. So let me put one tricky question. I want pi of 100.
So I didn't understand what pi of 100 means.
So pi
Sir,
of
it
100
is 5. Sir,
pi
it
of
is
100
5.
is just a minute. Pi of 100 is the number of primes up to 100. And how many we have calculated? There are 25. So it
How do you
Yeah.
calculate
So should we send the
Pi
answer
of
to the
pi of
chat or
100 is
tell me?
9, sir.
9.
9.
9.
if you
9.
add all these,
9.
that is 25, right? For 100.
The
Yeah.
pi of 25 is
It is
9.
9.
Okay, so how do we calculate this? So this is pi of, first we calculate
And we know that pi of
inside
sir,
bracket.
pi of 100 is nothing but 25, sir.
Yeah.
So pi of 25 is 4 plus 4 plus 1.
Just a
So
minute,
it's
let me talk to
9.
me. Yeah. So how do we calculate? We calculate inside bracket first. Fine. So that is pi of 100, and that you have already said as 25. So now we want pi of 25. Pi of 25. And now
9.
in fact,
4
4
plus 4 plus only one of the 2.
plus 4, 8, and only one of these, 23.
9.
So plus 1, 9. All of you agree that this is 9. So far, okay, everyone?
Yes, sir.
Sir,
Yes.
Sir, it is a smaller number, so we can just count it. If it is a larger number, and if somebody has to calculate the number of primes, so how can we calculate it?
Actually, it's a difficult thing because there is no exact formula for number of primes up to n, but a nice result which talks about in general the behavior of pi n is following. So it was due to Gauss.
Sir, you said that we can find out the number of primes by using the pi one.
Yeah, no, that function just defines how many primes are there up to n. So that
Yeah, it
does not
just knows how to
have
write
any
it.
formula. So more general result is about which gives you, of course, estimate, not the exact value. That is
Okay, sir.
prime number theorem
Okay, sir.
due to Gauss prime number theorem.
Sir,
In
I
fact,
have a doubt.
Ramanujan gave something very close to pi n. So there is some noise behind. Yeah, so prime number theorem says the number of primes pi n is approximately n by log n. But right now I'm not going into those details because I have to define various things like log n, etc. So
Log n base what?
log into base e. Yeah, it's from calculus. So this is natural log. Anyways, I'm not going into those details right now, but this gives you approximate value of pi, not exact value.
Sir, so you're meaning to say that prime numbers don't have a sequence to follow.
Yeah, there is no fixed formula for nth prime, or there is no precise formula for nth
So I
prime.
can simply prove why this formula is wrong, because n
Or-
graph is very straight, and log n graph is also very, I mean, predictable, means predictable, but prime number is very not predictable, so it will easily break after some time.
Which one? This one, n by log n? No, this is proved result, prime number theorem. It's a theorem that's proved already.
Yeah, okay.
Yeah, but it's approximate. I'm not saying exactly equal to. It's approximate. Yes.
Yes.
Or there is no nice formula using polynomial. There is no polynomial. There is no polynomial formula. Which gives all primes. Which gives all primes. Okay. Now for smaller numbers, what best we can do is there is nice technique called as sieve of Eratosthenes. Let's look at that.
Sir, can you go once to the
Yes.
page?
Yes. Just a minute.
Sir, just a minute. I'll just write it.
Anyways, you'll get all these PDFs later on that Google Classroom or whatever.
Yes, sir. Sir, it is finished.
Yeah. Okay. So what best we can do is in general, sieve of Eratosthenes. Eratosthenes was basically a librarian at Library of Alexandria. Where is Alexandria?
In Egypt.
Near Egypt.
Egypt. Yeah. And his period is in fact little before Euclid, so that is 276 BC to 194 BC, or almost the same period as Euclid. Yeah, and he's more famous, in fact, for his work on or his experiment on calculation of the circumference of Earth. So he calculated circumference of
Yeah, by putting a straight rod.
Yeah.
And there are some nice short videos on YouTube about how he did that experiment.
Sir, actually, I think you have done the sieve of Eratosthenes.
Yeah, but we'll do it again. So everyone may not know it. And he calculated circumference of Earth to a very great precision. So his answer was something like nearby 39,375 kilometers. And actual answer is the recent known circumference is actual answer. That is 39,941. And which means if you calculate error, so I leave it to you, find out error, and that is less than 1%. Error is less than 1%. So in those days, without much instruments, etc.
Wow, that's so long ago.
Yeah. But as someone said, in fact, using some big rod or something, he did a nice experiment.
Yeah.
Okay, anyways, coming back to primes. So what was his sieve of Eratosthenes? So idea is, so you cross numbers which are not primes, and numbers which are non-cross, they turn out to be prime. So cross the first number, because by very definition, 1 is neither prime nor composite. So cross 1, and the very first uncrossed number, that is prime. So 2 is prime. Then as someone said, once 2 is prime, multiples of 2, so they have proper divisor, namely 2 itself, and they are not primes.
Yeah.
Multiples of 2 are not primes, so cross all those numbers, 4, 6, 8, 10, 12. In fact, what you can do is, you can write down quickly numbers 1 to 100 in your notebook and go on doing this. Will you do that quickly? So rather than looking here, it's better you do yourself. So cross all multiples of 2. So let me cross it horizontally. All numbers which are even, they can't be prime.
Sir, it is easy. Actually, I have to cross the numbers which are ending with 2, 4, 6, 8, and
Yes,
0.
So I'm crossing it now horizontally. So here in this case, just as an example, we want it up to 100, and I've written numbers up to 100. But more generally, you can do it for any number n. And
You didn't cross out 48, 68, and 88.
oh, sorry, I crossed something wrong. No.
No, so you didn't cross out 48, 68, 80.
And obviously all multiples of 10 ending with 0, so they can't be prime. And now you see the first uncut number is 3, so 3 is prime. Again, as
Sir, and
someone,
the multiples of 3.
yeah, so again, as someone said, multiples of 3, they are again not going to be primes. So cross multiples of 3, and you see some multiples are already crossed, like 6, 12, and so on. Okay. So cross odd multiples of 3. Even multiples already we have done, because they are multiples of 2 also. 15, 21, 57, 33, 39, 45, 51, 57, 63, 69, 75, 81, 87, 93, 99. Have I crossed everything?
Just 2 minutes, sir.
Sir,
Yes, sir.
then you have to cross out all the numbers ending with 5.
Wait. Have I crossed correctly all multiples of 3?
Yes, sir.
Yes, sir.
So now the first uncut number is 5, and that is prime. Fine. And again, once 5 is prime, cancel out all multiples of 5. They can't be primes. So what are multiples of 5? Either ending with 5 or ending with 0, out of which those which end with 0, they are even numbers, and we have already crossed them, 10, 20, 30, 40, 50, and so on. So now I have to cross all odd multiples of 5 which end with 5. Again, some of them already they are crossed as multiples of 3. Yeah. So again, first uncut number is 7, and that is prime, because that is not a multiple of anything. In fact, in higher numbers, in higher maths, there are many such sieves available by various mathematicians.
So can I say one statement which this is one of the proofs for?
Which ones again?
Yeah. So for a number n, okay, like for a number n which is not too big, which you can calculate, if you want to find whether it's prime or not, you don't have to go to every number before it. You can only go till the square root.
Yeah, the
of
square
the
root of the
because the reason is because every factor, every like factor will usually have another pair, except when it is a square number, it will have a pair. For example, let's take a random number. Let's take 70. Okay, 70 has two factor. It has 7 and it also has 10. Okay, so
Yes.
just because 70's root is approximately
Second, better than 70, you take perfect square, like 100 or something. So that will be easy, because root 70 will be in
or 100 is also like very okay, fine, 100 is fine. So root of 100 is 10. Okay, so now we know that 100 is 5 times something. I mean, we can check 100, it's divisible by 5, and if it's divisible by 5, there'll always be one factor which is greater than 10, which is in this case it will be 20. So if we know that from 1 to 10 nothing is divisible by 100, we can also say that greater than 10 there won't be any other factor divisible by 100, because if there is, then if there is a factor greater than 10 which is divisible by 100, then its pair factor will have to be at least equal to or greater than, and when you multiply two numbers which is greater than 10, you will get a number greater than 100. So that's why.
yes. Okay, so what has Saket told? Let me tell it in a little simpler way. So for example, look at say 100. Suppose my number is 100, and if I want to check whether it's prime or not, I have to check by numbers up to root 10. So it must have some divisor up to root 10. If there is no divisor up to root 10, then it must be prime. That's what he says. And look at the idea. Like for example, when I factorize 100, so 100 is 1 into 100, or 2 into 50, or 5 into 20, or sorry, 4 into 25, 4 into 25, or 5 into
Can you
20.
just
So
repeat
see
that,
that,
sir? Can you just repeat what he said, sir?
yeah. So see that when I factorize 100, one of the numbers is greater than 10, right? One of the numbers is 10 or greater than 10.
Yes, sir.
So obviously,
Oh, okay. So the number
one factor
multiplied
will
by
be,
that is
yeah,
equal to
one
100.
factor will be less than or equal to root 10, and
Okay, sir.
other factor will be greater than root 10. So if there
Okay,
is
sir.
2 factor up to root 10, both factors can't be greater than root 10, right?
Yes, sir.
So if n has no divisor or factor up to root n, and by up to root n I mean the integer part of root n, not the integer part of root n, then n must be prime. N must be prime.
Or sir, you can take an example, though it is irregular, it will at least prove the point because it is prime. Take any prime number which is close to a perfect square, like 23. So 23's root is approximately 5. So we can calculate from 1 to 5. We calculate from 1 to 5. Obviously, we will find that there is no number from 1 to 5 which is divisible by 23. Now from there we can think, okay, the minimum factor which is greater than 5 will be 6, and if 6 multiplied by 6 itself, it's 36 already. Then from there only we can say that there cannot be any more whole number integer factor which is greater than 5.
Yeah. So again, coming back to our sieve, we haven't completed. So now you have to cancel out multiples of 7. Anything left? 49 is left.
Sir.
Sir, only prime multiples of 7, as in 7 into 7, because 7 is prime number, then
7.
7.
And
So
9.
91.
That's all, because 7 into 9 is not prime number, and they all will have other factors, no?
Okay, and now see that whatever left, they are all primes. So 11.
Yeah, because what
Sir, can you put it in a different color because it's a little confusing.
Oh, yes,
to
yes.
get it.
So what color should I use?
Sir, also can you
Sir,
put,
anything.
sir, can you put 1 in a box?
1 already I crossed. 1 is surely by definition not prime. Yeah. 19. What else? 23, 29, 31, and 37, 41, 43, 47, 53, 59. So if you have already written all these primes in the beginning, check whether you have written correctly or whether you have missed something. 67, 71, 73, 79, 83, 89, and 97.
Sir, I have a doubt, sir. Similarly, how to find the prime numbers till 500?
Just a minute, just a minute. Kavin, 2 is prime by definition, right?
Yes, sir.
Someone was asking something. Somebody
So
was
that person was asking that how do we find prime numbers up to 500 or some number?
oh, same method. I mean, use this same technique. Only thing you have to cut multiples of numbers up to root 500. Fine. So
Yes.
root 500 is roughly like you have to cut multiples of up to 23.
Sir, could you repeat it again?
See, same technique. Whatever we have done for 100, only thing in this case we erase we cut multiples of primes up to root 100. That is said. to 10. So up to 10, how many primes were there? 2, 3, 5, 7. And we cancelled out multiples of 2, 3, 5, 7. And what are left? They are all primes. Okay, so same technique. Only thing for 500, you have to go up to root 500. Root of 500 is approximately 24 point something.
Yes, sir.
So maybe you have to cancel out multiples of primes up to 23. So cancel out multiples of 2, 3, 5, 7, 11, 13, 17, 19, 23. I think even 23 is above 500. Root 23, root of 500 is less than 23. Yeah, so far good. Shall we go ahead?
Yeah. Yes.
Okay, so you are given some numbers. Check which of them are primes and don't disclose answers. You can write down answers in chat box.
Sir,
Yes.
sir, are they like that? Are they Are they dashes or minus symbol?
Minus. So let me explain the question. So first number 2 square minus 1. And what do I mean by 2 square? 2 square is 2 into 2. 2 multiplied 2 times. So that is 4 minus 1. And clearly you see this is prime.
Sir, it is difficult for us to write square, and also we'll just write the number. Like we say 1, we mean the first one is prime. If we mean 7, we mean the 7th number is prime.
No, you simplify all these numbers and you work out. So 2 cube
Oh,
minus
okay. Yeah. Okay, like that. Okay.
so 2 cube is 2 into 2 into 2 3 times. So that is 8. 8 minus 1. That is 7. 7 is again prime. Is the question clear to everyone?
Sir, I don't understand how to give the answer.
That's so.
Sir,
Yes.
I don't understand how to give like type the answer, sir. How exactly is it?
Yeah. So in fact numbers are not directly given. You are given in terms of power. So like for example, what do I mean by 2 raised to 4? It's 2 into 2 into 2 4 times. So that is 16 and 16 minus 1. So 2 raised to 4 minus 1. Right? So that is 16 minus 1.
So like, should we write 2 raised to 2 minus 1? If one of the things is a prime, for example, 2 square minus 1 is a prime. So do we write 2 square minus 1 or?
Oh, just 3, sir.
Sir, is there a pattern, or do we have to individually evaluate?
So do we write like
No,
3 or do we write 2
you
square
have to
minus 1?
evaluate individually. They're typical kind of numbers and they have some special names. So I have given all of them.
So we can just like write 3, 7 like
Yeah,
that.
so what I don't know how you can write in chat box, but maybe you can use some symbol for that exponential, something like this. I don't know.
So 2 power 2.
Something like this. Just
So can we just like 3 for 2 2 squared minus 1 7
right.
for 2 cube minus 1.
Yeah. 2 power 8 minus 1, something like this. Okay. That 2 raised to 4 minus 1, that is 16 minus 1, which is 15, and 15 is not prime. It's 3 into 5, right? It's composite. Then I go ahead. 2 raised to 5 minus 1. That is 32 minus 1. That is 31. 31 is prime. Already a list of primes up to 100. You can check that. Then 2 raised to 6 minus 1.
63 is not prime.
That is 64 minus 1. 63.
It is divisible by 3.
3.
Yeah, so it's 9 7 that fine. So it's not prime. Now the numbers exceed 100. So if at all it's prime,
So it is 128. 64 multiplied by 2.
4 to the 128 minus 1. So that is 127.
Short is is a prime number.
That is a prime number, sir.
Yeah.
How to find whether 127 prime? You have to do it manually.
Yeah. So for 127, you have to check by numbers up to root 127. Fine.
Sir, up
Root-
till
I
11,
thought there
sir,
was a
because
pattern.
approximately it is 11.2, sir.
Check 2, 3, 5, 7, and 11. 13 is above root 127.
Yeah, sir, but can I say something, sir? These all these 2 power odd number minus 1 we can manually check, but we don't have to check 2 power even number minus 1. So any 2 power even number greater than 2, okay, so they will not be a prime, because any like, for example, let's pick any even number greater than 2. Let's pick 14. Okay, so 2 power 14 is the same as 2 power 7 squared, and when we know that 2 power 7 squared is equal to 2 power 7 minus 1 into 2 power 7 plus 1. So we already know 2 factors greater than 1 and less than the number. So we can say it is not.
Yeah, so Saket is saying 2 raised to even power minus 1 can't be prime. It can be factored. Fine. Saket, can you say something more about that power n? When
Yeah, I mean, looking at the pattern right now, if n is prime, then 2 power n minus 1 is prime number, and if n is not prime, 2 power n minus 1 is not prime. I mean, it's a pattern, but I don't know why reason.
yeah, so complete all that list and then observe something.
So what?
Complete list of all these numbers up to 2 raised to 11, and then we can observe something. 2 raised to 8 minus 1, that is 256 minus 1, that is 255. 255 is obviously not prime because it ends with 5, so it's divisible by 5. What about 127? That is prime.
Sir, 127 is prime, sir.
Then 2 raised to 9 minus 1, that is 512 minus 1, that is 511. What about 511?
Divisible by
It's
7,
not
sir.
prime, divisible by 7.
Yeah, so 7 divides this, so it's not prime. Two raised to 10 minus 1, that is 1
Sir,
0.
1024 minus
Sir,
1023, sir, it's divisible by 3.
Yeah, so as in fact Saket told, once power is even, it's not a prime. So this is surely not prime. And you can quickly check it's divisible by 3 by what a test of divisibility for 3.
Sir, yes, sir, yes, sir.
Okay.
The next is 2048 minus 1, 2047.
Yeah, now let me tell you something interesting. In fact, Mersin studied these kind of numbers. Yeah, shall I go to next page?
Yes, sir.
Mersin studied these type of numbers, 2 raised to some n minus 1, right? And like Saket observed for even powers. In fact, what Mersin observed was if n is composite, then obviously 2 raised to n minus 1 is not a prime. If n is composite, 2 raised to n minus 1 is not prime. But in fact, some tricky things are if n is prime, sometimes it is prime, sometimes not. 2 raised to n minus 1 is not always prime, sometimes it is prime, and sometimes not. Okay, and he gave some such examples up to 200 something.
So general proof, can you give?
No, for so you want it for a composite?
Yes, sir. For not
Yeah,
for
yes, we'll be doing that, but little later once we do some algebra part. So we need.
Sir, can I try to prove this for composite?
I sent you an answer.
Yeah, but we won't do it today. We'll do it
So
after.
will it be like a to the power n minus b to the power n formula?
Yes. So we need some formula. We need some algebra. Okay. So in fact, the interesting numbers are when n is prime, but 2 raised to n minus 1 is composite. And one such very first example was 11. So check that 2 raised to 11 minus 1 is composite. This is not prime.
2 raised to 11 is 2000. 2 raised to 11 minus 1 is 2047.
2047.
Yes, so factorize 2047. And in fact, based on these ideas for higher values of n,
The composite of n.
we use such numbers in crypto systems, in fact, like RSA systems.
Sir, actually, how is 2047 composite?
I don't know, you factorize it. So essentially,
I noticed something with 2 power n minus 1. So is equal to, like, if it 2 power n minus 1 is equal to 1 plus 2 plus 4 so on till 2 power n minus 1 in brackets, like.
but that's not going to help for a factorization.
Yeah, just because 1 is there. If 1 was not there, we can take 2 common out and prove generally. But
Yes, Agneya?
Sir, so you're saying that 2 power 11 minus 1 is composite?
Yeah.
Okay, sir.
And in fact, the idea is in general, factorization is in general difficult. And whereas if I give you some two numbers to multiply, that's always easier. And just based on this concept, based on this idea, there are some public key crypto systems, so called as RSA crypto system.
sir,
Yes.
using this, you can find very large wait, no, you can't. Sorry.
Yeah, in fact, on internet there are groups. So there is a group called as GIMPS, or it's a project, GIMPS. So that's called as Great Internet Mersin Prime Search. Great Internet Mersin Prime Search. So if you are good at coding and number theory, you can also join that group. And collectively, they keep on finding large and large Mersin primes. So recently,
Sir, you told this actually.
Yeah.
I remember.
Yeah, so latest known greatest prime is Mersin prime is latest known Mersenne prime. So we'll denote it as MP is 2 raised to 82589933 minus 1. So this was found in 2016. Found in December 2016. I don't think after that they have searched or they have got some new prime. So in general, it's difficult to find such primes.
Sir, is there a pattern as to what type of prime number will lead to 2 power n minus 1 also being prime? I mean, I'm sure that there's some logic behind it.
No, in general, there is no such if and only if result, but there are certain one-way results that if at all.
Okay. I mean,
It's,
if there is a way, yeah, like for example, if we can further do something like prime, if it is this type of prime, then for sure 2 power n minus 1 will be prime. If it's not this type of prime, then it will maybe prime or maybe composite. Then using that, we can find the largest prime number we can do all that stuff.
Yeah, unfortunately, there are no if and only if results, both way results. Only there are one-way results. But surely what's known is there are infinite many Mersenne primes.
Yeah, yes.
Okay, shall we go ahead?
Yes.
Everyone, shall we go ahead? Anybody has any
Yes,
doubts?
sir.
Yes.
Yes,
Okay,
sir.
but yeah, just a minute, but nobody told me what is 2047. 2047 is? I want
Sir, it
factors.
is a prime number.
No, it's not prime. I want factors.
We can wait. Even if we find the root of 2047, still there are a lot of numbers.
Yeah.
I think, wait, let me try common, like 7 number, like 7. Let me try.
6, 7. Surely 2, 3, 5 won't divide, 11 won't divide. 6, 7. Or 13.
Yes, sir. 2047 is not a prime number. It is a composite.
What are the factors?
Sir, it is not divisible by 7.
Yeah, 7 does not divide.
Oh,
Sir, maybe it is a multiple of a prime number.
So it's a multiple of 23, sir. It's a multiple of 23 divides, sir.
Yes, so it's 23 into 89. Check.
Sir, yeah, sir, that's what I was telling, that it is a multiple of
Okay,
prime.
now let me tell you, if I give you a question like multiply 23 and 89, within few seconds, all of you will multiply and get answer 2047. But if I give you 2047 and ask you to factorize as product of primes, then it will take at least a minute.
So this is how encryption works,
and
sir.
the most funniest
A
part,
gigantic prime and you try to factorize it.
Yeah, and based on
and
this,
the most funniest part is that 2047 can be factorized in many different ways, but 23 to 89 will only give us one answer, and yet we can calculate 23 into 89 faster than 2047.
Saket, just a minute. So, what do you mean by you can factorize it in many ways?
No, means usually, I mean, in this case,
Or I mean different methods. That's what you want to say. Because
yeah. So factorizing 47 can be like a different like numbers, like just like you can factorize 20 as 4 and 5 and 2 and 10 like that, but multiplying 4 and 5 will only give 20. And yet still if we multiply and there's only one possible answer, it's easier to get that one possible answer than to get one of many possible answers.
No, in fact, in this case, luckily both 23 and 89 they are primes, and if you factorize the number as product of primes, that's always in a unique manner, unique way. So there are no more than one ways.
Okay. In this case, the general.
Yeah. Okay, shall we go ahead?
Yes, sir.
So far, everything is fine? Yeah. Alice was 2 years younger than Bob. If they lived for 100 years, how many times ages of both were prime numbers?
So they live for 100 years, meaning 100 years in total or 100?
Up to 100. No, no, individually both lived for 100 years.
Sir, I sent my answer. Is it correct?
Sir, it means that both of them lived for 100 years.
Okay, just a minute. I'll explain the question. So what we want is Alice age is prime number, and Bob is 2 years elder than Alice. So if Alice is T years old, Bob will be T plus 2. Right? So we want how many times up to 100 both P and P plus 2 are primes. Is the question clear?
So one example is 59 and 61.
No, why? 3, 5.
5 and 7.
One
sir,
example.
5 and 7. Sir, 5 and 7.
Yeah, so 3, 5,
59 and 61.
Oh, sir.
3, 5, 5, 7.
3, 5, 5, 7, 11, 13,
13.
17, 19.
Johan,
No, it's just the number of twin primes that are under the 100.
very good, very good. So that's what I was going to tell you. So in fact, such numbers are called as
29 and 31.
such numbers are called as twin primes. So if P and P plus 2 both are primes,
We can forget the question and just calculate how many twin primes are there from 1 to 100.
Yes, they are called as twin primes. Now let me tell you one question which is still unsolved. So there is one question which is still unsolved. It's a conjecture. So what do I mean by conjecture? One which is neither proved nor disproved. So nobody yet knows the exact answer. Conjecture. There are infinitely many twin.
So this is the Goldberg conjecture, right?
No, this is not good.
Oh, okay.
There are infinitely many twin primes.
Right, this is the twin prime conjecture, sir.
Yeah. So maybe if some of you get interested in number theory and later on if you become a number theorist, so here is one open question.
So basically twin primes are two prime numbers which have one composite number between them.
Sir,
Yes.
I don't think there are infinity many twin primes.
Sir, is my answer correct? I sent you the answer. Agne.
Okay, just a minute. In fact, question is easy. So
Sir, it is even more easier because the previous problem we did was about prime numbers. So actually we wrote all the prime numbers between 1 and 100.
Yeah, so if you have written all primes between 1 to 100, then question is simple. So you have to just note from that list where P and P plus 2 both are primes. I think there are 8 such pairs. Right? 8 pairs.
Yes, sir.
Or 8 times. 11, 13, then after
17, 19.
19,
17, 19,
Sorry, then 29 and
29,
31.
31,
29, 31.
41, 43.
41, 43, 71,
Sir, 41, 43, sir. 59, 61. Sir. 71 and 71, 73. That's also. 71, 73.
that's also.
And that's it, sir.
Yeah, that's it. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So count it. Total there are 8 times. Both ages of both must be prime numbers. So there are 8 twin prime pairs up to 100. Fine.
Sir, but in 3 and 5 is already used. Why do you have to repeat it and say 5 and 7?
No, when I count 3, 5, P is 3 and P plus 2 is 5. But when I count 5, 7, P is 5 and P plus 2 is 7. So they are different.
Okay.
They are counted as different pairs.
Oh, okay. Okay, sir. Thank you.
Okay, shall we go ahead?
Yes,
Yes,
sir.
sir. 1 minute, sir. Sir?
Yes.
Sir, I thought you were not there.
No, I'm waiting. Somebody said to wait.
Okay, sir.
Okay.
This is the Goldberg conjecture, sir.
Yes, yes. Very good.
So can I say?
Just a minute. Let me say something.
Sir, can I say too?
Sir, I sent my answer in the
Sir, it
chat.
is 97.
Sir, I sent my answer in the chat.
Yeah, so this is question. The question is simple. This is question based on a well-known conjecture that's known as Goldbach conjecture. And it's again unsolved problem for about more than 300 years. Goldbach conjecture.
Sir, for now it is an unsolved problem for just 2 or 3 minutes.
Yeah. So what Goldbach conjecture says, again it's a conjecture. And what's a conjecture? A statement which is not proved and nor even disproved. Right? Okay, so what it says,
Conjecture meaning?
Conjecture is a statement which is neither proved nor disproved. Disprove means you have to give some counter example. So there is no counter example found, as well as
Sir, is there an example?
Yeah, just a minute. Let me write the statement, then we'll go to that. Okay, so statement is every even number n greater than 4. Every even number n greater than 4 can be expressed as a sum of 2 primes. So for example, 4 I can write as 2 plus 2. 6 I can write as 3 plus 3. they may not be distinct. 8 I can write as 3 plus 5, or 10 I can write as say 5 plus 5, or as well as 3 plus 7. So it can be written in two ways. Is the statement clear? And this statement, they have checked for numbers up to I think some 1 million or something, and till that number there is no counter example found, which means every even number they could express as sum of two primes.
Yeah, sir. I said my answer long ago. Sir, did you check it?
So is my answer
No,
correct?
I haven't checked yet.
Sir, is my answer correct?
But anyway, the solution is, I mean, answer to this is simple. So 100 we can write in various ways as sum of two primes, but the question is
97 plus
on
3.
Goldbach conjecture.
Sir, actually, it is not a very long process. Sir, we just have to take the prime numbers from 1 to 100, and we should start from the back. We should start from 97 and then
Yeah,
89.
just a minute. So you said start with 97. Okay, 97 plus 3, and 3 is luckily prime, so this is one
Yes,
such
sir.
pair. Yeah. Then
Sir, and then we have to go back from the latest number. So
yes,
it is 89.
yes.
Sir, we can't, there is no other number.
And 89 plus 11. Again, luckily 11 is
Yeah,
prime.
yes, sir.
You can write 100 as sum of two primes, at least in two different ways.
Yes, sir.
Is there any other answer?
Sir, and then we should again go back to 79.
Huh?
But we
Sir,
79
93.
plus 21 is equal to 100. So
21
it
is
can't be. And
Sir, she forgot 93.
Sir,
It
83.
can't
Sir.
be.
Yes, sir. She
Just
forgot
a minute.
83.
Just a minute. 93 is not prime.
Sir, actually it's
83,
sir,
sir.
not 93.
83.
83.
No. 8.
83 plus
23
17.
plus 17.
Yeah, 83 plus 17 works.
So can't 59 plus 41.
So there's some noise coming.
Yes. Somebody's audio is on.
Yeah, just stop.
Sir,
Then
71 plus 29.
Yeah,
okay,
sir.
71 plus 29. Good. Yeah. What
So
else?
that 53, sir, 59 plus 41. 59 plus 41.
89 plus 11. 53 plus
Sir,
40.
53 plus 47.
Sir, also 69 plus 31, sir. So
53 plus 47.
Divisible by 3.
Is there anything left?
Sir, I don't think so.
Yeah,
No,
so
sir.
100 we can write as sum of two primes in two different ways, in 6 different ways, right? So there are 6 ways. But I mean, it was simple. So anyway, it's related to a nice unsolved problem in number theory, and that is Goldbach conjecture. So what it says is every even number greater than or equal to 4 we can express as sum of two primes. And so far there is no logical proof found, as well as there is no counterexample found. What do I mean by counterexample? So nobody has found some even number greater than 4 which cannot be expressed as sum of two primes. Okay. Recently there are many developments towards the proof of Goldbach conjecture, but so far nobody has established.
Sir, you can, so someone can just use the computer to find out and run till until a counter example is found.
Yeah.
The computer can't do it, then it must be.
So I think latest known result is following. Every such even number greater than 4 you can express as one prime, and the other number which is product of two primes. So it's of the form P plus Q. That's the best known result so far.
So what? So what?
One prime and the other number which is product of two primes.
But product of two primes is composite.
Yeah. So that's what. Still, it's not proved. So what's best known is, in fact, every such n you can express as sum of one prime and the other number which is not prime but maybe product of two primes.
Sir, why
That's
can't
what is
it be
proved. That's what is known. That's what is proved.
Sir, n is even or n is any number?
Even n is even.
So for n equal to even, we can write it as p plus qr. Is it?
Sir, I have a doubt. Sir, I have a doubt.
Yes, I agree.
Sir, is one a composite number?
Neither composite nor prime.
Even number greater than 4 is composite always.
Okay. So then what is one?
Neither composite nor prime.
One is neither prime nor composite. That's what we said in the beginning.
Sir, as numbers get larger, prime numbers, appearance of prime number is very low. The frequency is very low. Is it
Yes.
possible at one point of time, in the stretch of infinity of numbers, prime numbers don't appear at all?
That is not possible. In fact, that is proved that there are infinitely many primes. So that is proved. And if you look at the internet, there are almost more than 100 proofs of this fact.
It's a what if you ask ChatGPT?
I don't know much about ChatGPT, and ChatGPT, in fact, ChatGPT failed in some Singapore maths grade 5 exam, or even as well as it fared very poor in UPSC exam. So I don't believe on ChatGPT.
Sir, people are saying it passed JEE exam. I don't know. Its information is from the internet, so you don't know.
Okay, so now in this PDF, there are many problems later on after this, and they are all as homework. So you try all those problems, work fair amount of time. And except last one or two problems, all are simple. Okay, so we'll stop them for today. Fine.
So what problems are we supposed to do?
So try to solve all those problems as homework. So what are left? And later on, if you have some doubts, we'll take it later. But
So which problems, sir? Which problems, sir?
After this, there are many problems in this PDF. So 6,
Okay.
7, 8, 9, 10, 11, 12.
Okay, sir.
So they are all homework. Try them.
So where will you upload them in the Google Classroom? Sir, will you upload it in the Google Classroom?
Yes.
Okay, sir.
Okay, then.
Can we leave?
Yes. Bye, everyone.
Okay, sir. Bye, sir. Thank you, sir.
Bye, sir.
Thank you.
Thank you, sir.
Bye, sir.
Thank you, sir. Bye, sir.
Thank
Bye,
you, sir.
sir.
Bye, sir.
Sir, the extra
Bye,
problem
sir.
for homework will be uploaded, no?
Yes.
Sir, bye, sir.
Okay. Bye, sir. Thank you, sir.
Thank you, sir. Bye, sir.
Bye, sir.
Yeah, bye.